Hello everyone. This time we will discuss systems of linear equations in three unknowns. I am Catherine I. Merca from the Department of Mathematics and Statistics, College of Science and Mathematics. Our learning objectives are as follows. At the end of the lecture, students should be able to solve systems of linear equations in three unknowns and identify inconsistent systems of equations containing three variables. A system of three linear equations in three unknowns, x, y, and z, can be expressed as a sub 1x plus b sub 1y plus c sub 1z equals d sub 1, a sub 2x plus b sub 2y plus c sub 2z equals d sub 2, and a sub 3x plus b sub 3y plus c sub 3z is equal to d sub 3, where a sub 1, a sub 2, a sub 3, b sub 1, b sub 2, b sub 3, c sub 1, c sub 2, c sub 3, and d sub 1, d sub 2, d sub 3 are all constants. The solution set to a 3 by 3 system is an ordered triple XYZ. Graphically, the ordered triple defines the point that is the intersection of three planes in space. You can visualize such an intersection by imagining any corner in a rectangular room. A corner is defined by three planes, two adjoining walls, and the floor or ceiling. Any point where two walls and the floor meet represents the intersection of three planes. The following are the possible solution scenarios for 3 by 3 systems. Systems that have a single solution are those which, after elimination, result in a solution set consisting of an ordered triple XYZ. Graphically, the ordered triple defines a point which is the intersection of three planes in space. So here's the sketch of three planes which intersect at a single point, which is represented by 3 by 3 system with a single solution. We have here the point of intersection wherein is the first plane. The second plane would be the plane which is colored violet, and the other plane is the plane colored green. Notice that they meet here at this point of intersection. Now, systems that have an infinite number of solutions are those which, after elimination, result in an expression that is always true, such as 0 is equal to 0. Graphically, an infinite number of solutions represents a line or coincident plane that serves as the intersection of three planes in space. So here's the sketch here of three planes that intersect in a line representing by a 3 by 3 system with infinite solutions. So notice that the intersection is actually a line. So we have the first plane is colored violet here, the second plane is colored blue, and the third plane is colored green. Now, systems that have no solution are those that, after elimination, result in a statement that is a contradiction, such as 3 equals 0. Graphically, a system with no solution is represented by three planes with no point in common. The following three figures represent 3 by 3 systems with no solution. So the first one here, A, is a representation of three planes that intersect with each other, but there's no common point. The second one, B, we have here two planes which are actually parallel and intersect with a third plane, but not with each other. Then, the last one here is a representation of planes which are parallel, but there is no point of intersection. Now, here are the steps in solving linear systems in three variables. The first step is to choose two different pair of equations and eliminate the same variable for both pairs. This will reduce the system to two equations in two unknowns. Then, the next step is to solve the resulting system of two equations and two unknowns using elimination or substitution method. This will result in an equation in one unknown. And then solve the resulting equation in step 2. Substitute the value obtained in step 3 into either two equations and two unknowns to find the second variable. And then to find the value of the third variable, substitute the values of the two variables obtained in step 3 and step 4 to any of the three original equations of the system. And then lastly will be to verify whether the three values obtained satisfy the three original equations. Recall that a solution to a system of linear equation in three variables is an ordered triple of real numbers x, y, z that satisfies all three equations of the system. The graph of each of the linear equations in three variables is a plane in a three-dimensional coordinate system. Graphically, a solution to this system is the intersection of these three planes. Now, the first example here is to find the solution set of the system for x plus 3y plus z is equal to 15, x minus y minus 2z is equal to 2, and 2x minus 2y plus z is equal to 4. So here are the steps and the solution. Number 1, choose two different pair of equations and eliminate the same variable for both pairs. This will reduce the system to two equations in two unknowns. But first, let us denote the equations by e sub 1, e sub 2, and e sub 3. So we have here our e sub 1 as 4x plus 3y plus z is equal to 15. E sub 2 is x minus y minus 2z is equal to 2. And e sub 3 is 2x minus 2y plus z is equal to 4. Now let us choose equations e sub 1 and e sub 2 and eliminate z. We do this by multiplying 2 to both sides of equation e sub 1, so that we now have 2 times e sub 1 will give us, we have 4x here plus 3y plus z is equal to 15 for e sub 1. So it becomes 8x, 6y plus 2z is equal to 30. And since our e sub 2 is x minus y minus 2z is equal to 2, when we add the two equations, we come up with 9x, this is 6y minus y is 5y, and 2z minus 2z is equal to 0, so 30 plus 2 will give us 32. Now let us denote the resulting equation to variable by e sub 4. That is, our e sub 4 now is 9x plus 5y equals 32. And then we choose another pair of equations, say e sub 1 and e sub 2, and eliminate the same variable z. We do this by multiplying -1 to both sides of equation e sub 3 as seen below. Thus, adding the two equations, we now have the following. So we have e sub 1 is 4x plus 3y plus z is equal to 15. Then multiply -1 to e sub 3 will give us minus 2x plus 2y minus z is equal to -4. So 4x minus 2x will give us 2x, 3y plus 2y will give us 5y, z minus z will give us 0, 15 minus 4 is equal to 11. So let us denote the resulting equation 2x plus 5y equals 11 by e sub 5. So e sub 5 now is 2x plus 5y equals 11. So solve the resulting system of two equations and two unknowns using elimination or substitution method. And this will result in an equation in one unknown. And then we solve the following system. E sub 4 is 9x plus 5y equals 32. E sub 5 is 2x plus 5y equals 11. So notice that we can eliminate y by multiplying -1 to e sub 5 and adding the resulting equation to e sub 4. That is, e sub 4 is 9x plus 5y equals 32. Multiply -1 to e sub 5 will give us minus 2x minus 5y equals minus 11. And then adding them will give us 9x minus 2x is 7x. 5y minus 5y is 0. 32 minus 11 is equal to 21. Solve the resulting equation in step 2 and come up with the following. That is, 7x is equal to 21. So we can divide both sides by 7 and come up with x equals 3. Then substitute the value obtained in step 3 into either of the two equations in two unknowns to find the second variable. So we can solve for y by substituting x equals 3 to either equation e sub 4 or e sub 5, and then choosing equation e sub 5, we have the following. That is, e sub 5 now is equal to 2x plus 5y equals 11. We substitute x equal to 3. We have 2 times 3 plus 5 times y equals 11. Then solving for y, we have here, since we have 6 plus 5y equals 11, we can subtract both sides by 6 and come up with 5y equals 5. Dividing both sides by 5, we now have y is equal to 1. To find the value of the third variable, we can substitute the values of the two variables obtained in step 3 and step 4 to any of the three original equations of the system. Then to solve for z, we can now substitute x equal to 3 and y equal to 1 to equation 3. And then you can also choose e sub 1 or e sub 2, so that when we substitute the x and y values, we now have the following. E sub 3 is 2x minus 2y plus z is equal to 4. So substituting x equal to 3, we come up with 2 times 3 minus 2 times y is 1. So we have 2 times 1 plus z is equal to 4. And then solving, we now have 2 times 3 is 6. 2 times 1, we have 2 here, but that's minus. Plus z is equal to 4. So this is 6 minus 2 is 4. Plus z is equal to 4. We can subtract both sides by 4 and come up with z is equal to 0. So now, we verify if the three values obtained satisfy the three original equations. So checking the values, x equal to 3 y equal to 1 and z is equal to 0, if it satisfies the three original equations, we have e sub 1 is 4x plus 3y plus z is equal to 15, e sub 2 is x minus y minus 2z equals 2, and e sub 3 is 2x minus 2y plus z is equal to 4. Doing that, when we substitute, we have the following. Since e sub 1 is equal to 4x plus 3y plus z is equal to 15, we can have x equal to 3 here for x, y is equal to 1 for y, and z is equal to 0 for z. So that's equal to 15 there. For e sub 2, this is true because we have 4 times 3 plus 3 times 1, that is 12 plus 3, that's 15. Similarly, when we verify with e sub 2, e sub 3, we have two values. So meaning to say, we have here the solution set is at 3, 1, 0. That is, x is equal to 3, y is equal to 1, and y is equal to 0. This is a point in a three-dimensional coordinate system. And to visualize this solution set, we have the following sketch. Now, sketching of planes is not in our topic, but this will be discussed later. So, if you take a look at this graph, it's just to visualize the solution set. We have x is equal to 3, so this is at 2, this is at 3, then y is equal to 1, so you count 1, and then z is equal to 0. So this is the point here of intersection. The intersection of these three planes is this point, which is 3, 1, 0. So we have another example, that is find the solution set of the system 2x plus 2y minus z is equal to 5, x minus y plus 3z is equal to 2, 5x plus 2z is equal to 7. And we have the following steps and solution. First one here is to choose two different pair of equations and eliminate the same variable for both pairs. And this will reduce the system to two equations in two unknowns. So first, let us denote the equations by e sub 1, e sub 2, and e sub 3. So you choose e sub 1 to be 2x plus 2y minus z is equal to 5, e sub 2 as x minus y plus 3z is equal to 2, and e sub 3 as 5x plus 2z is equal to 7. Note that our goal is to reduce the given system into two variables. Notice that equation 3 only contains, this time, two variables. Take a look at this. So you only have two variables, x and z. Thus, we don't need to choose two different pair of equations to reduce the system. What we do is to eliminate the variable y in equations e sub 1 and e sub 2 in order to get another equation in terms of x and z. To do this, we multiply to both sides of e2 to eliminate y. That is, we now have the following. E sub 1 equals 2x, 2y minus z is equal to 5. And we multiply 2 to e sub 2. We have 2x minus 2y plus 6z is equal to 4. So that when we add them, we have 4x. And this one, 2y minus 2y is 0. Minus z plus 6z is 5z. 5 plus 4 is equal to 9. Denote the equation 4x plus 4z equals 9 by e sub 4. And pair this equation e sub 4 with equation e sub 3. Then solve the resulting system of two equations in two unknowns using elimination or substitution method. This will result in an equation in one unknown. Now let us solve the system e sub 3, 5x plus 2z equals 7, and e sub 4, 4x plus 5z equals 9. So we can eliminate z by multiplying both sides of e sub 3 by 5, and negative 2 on both sides of e sub 4. Then add the resulting equation to e sub 4. This will give us the following. 5 e sub 3 will now become, since e sub 3 is 5x, so we have 5x times 5 will give us 25x, 2z times 5 will give us 10z, and 7 times 5 will give us 35 here. So multiplying negative 2 to e sub 4, you have 4x for e sub 4 here, so you have negative 8x, 5z, that becomes minus 10z, and 9 times negative 2 will give us negative 18. And adding, we come up with 25x minus 8x is 17x. This is 0, and we have 35 minus 18 equals 17. So we now solve the resulting equation in step 2. So solving for x in 17x is equal to 17. We can divide both sides by 17, can up with x equals 1. And then substitute the value obtained in step 3 into either of the two equations into unknowns to find the second variable. So substitute x equal to 1 to e sub 3. We now have 5x plus 2z is equal to 7 to solve for z. So e sub 3 now is 5x plus 2z equals 7. You substitute x with 1. Come up with 5 times 1 plus 2z equal to 7. So solving for z, we come up with z is equal to 1. To find the value of the third variable, substitute the value of the two variables obtained in step 3 and step 4 to any of the three original equations of the system. To solve for y, substitute x equal to 1 and z is equal to 1 to e sub 2 x minus y plus 3z is equal to 2. So here we have x here is replaced by 1, and then we have minus y plus 3 times z is replaced by 1. So that's equal to 2. So we have 1 minus y plus z is equal to 2. And solving for y, we have here y is equal to 2. Now verify whether the three values obtained satisfy the three original equations. So check the values x equal to 1, y equal to 2, and z is equal to 1 if this satisfy the three equations. So the original equations are as follows. E sub 1 equals 2x plus 2y minus z equal to 5. Our e sub 2 is x minus y plus 3z is equal to 2. And e sub 3 is 5x plus 2z is equal to 7. So when we substitute the values, we have now 2 times 1, since our x is equal to 1. 2 times 2, since our y is 2 here. And then z is equal to 1, so you have minus 1. Now if you verify the three equations, it will come up to be true. Meaning to say, our solution set is the set containing x equal to 1, 2, and 1. And to visualize this solution set, we have the following sketch. You have here the sketch containing all the three equations, 2x plus 2y minus z is equal to 5. Then we have equation 2 is x minus y plus 3z is equal to 2, represented by this plane here. And this plane is the equation 3. This plane is equal to equation 1. So our solution set earlier was 1, 2, 1. If you take a look, you now have your x is equal to 1. Then move 2 units to your y, positive y, and then 1 unit to your x, to z. So this is our point of intersection, this corner here. Now, as I've said earlier, sketching is not part of our lesson, but sketching will be discussed later on. This is just for you to visualize the solution set. But this was a sketch making use of GeoGebra, an online sketching app. So finding the solution set to a dependency of equations would be for our example 3. You're asked to find the solution to the given system of three equations in three variables: 2x plus y minus 3z is equal to 0, 4x plus 2y minus 6z is equal to 0, and x minus y plus z is equal to 0. Here are the steps and the solution. So the first step is to choose two different pair of equations and eliminate the same variable for both pairs. This will reduce the system to two equations in two unknowns. So first, let us denote the equation by e sub 1, e sub 2, and e sub 3. So denote e sub 1 by the first equation, 2x plus y minus 3z is equal to 0, e sub 2 as 4x plus 2y minus 6z is equal to 0, and e sub 3 as x minus y plus z is equal to 0. And then we can multiply equation e sub 1 by negative 2 and add it to equation 2. So we have negative 2 times e sub 1. Since e sub 1 is this quantity, becomes minus 4x minus 2y, and then plus 6z is equal to 0. And because e sub 2 is 4x plus 2y minus 6z, so we have it here equal to 0. When we add them, minus 4x plus 4x is 0, minus 2y plus 2y is equal to 0, plus 6z minus 6z is equal to 0. So this is equal to 0 equals 0. Now, we do not need to proceed any further. The result we get is actually an identity, which tells us that this system has an infinite number of solutions. So in finding the solution to a dependent system of equations e sub 1, e sub 2, e sub 3 as given, there are other ways to begin to solve this system, such as multiplying equation e sub 3 by negative 2 and adding it to equation e sub 1. We then perform the same steps as above and find the same result, 0 is equal to 0. But when a system is dependent, we can find general expressions for the solutions. Adding equations e sub 1 and e sub 3, we have the following. So e sub 1 is 2x plus y minus 3z is equal to 0. E sub 3 is x minus y plus z is equal to 0. So that when we have 2x plus x, that will give us 3x. Y minus y is 0. 3z plus z is equal to minus 2z. And then we can actually solve for the equation. Solving for z, we have 3x minus 2z is equal to 0. But this will give us the value z is equal to 3 over 2x. So we back substitute the expression for z into one of the equations and then solve for y. So we now have 2x plus y minus 3 times this is our value for z earlier, that is 3 over 2x equals 0. Further solving will give us the following. 2x plus y minus, this is 3 times 3, it's 2. 3 times 3, that's 9. Then we have 2 here. So we have minus 9 over 2x equal to 0. Therefore, from there, we can now have y equals 9 over 2x. Then we have transpose minus 2x on the other side. So we have 9 over 2x minus 2x. So we're solving for this quantity. That will give us now the value y equals 5 over 2x. So the general solution is x, 5 over 2x, 3 over 2x. In this solution, x can be any real number, and the values y and z are dependent on the value selected for x. So as illustrated below, two of the planes are the same and they intersect the third plane on a line. The solution set is infinite as all points along the intersection line will satisfy all three equations. So this is the sketch. If you take a look at this sketch here, we have this plane. It's represented by negative 4x minus 2y plus 6z equal to 0 and 4x plus 2y minus 6z is equal to 0. They're the same plane here. And this plane is x minus y plus z is equal to 0, and they intersect on a line. Now we have another example, which is solving an inconsistent system of three equations in three variables. You're asked to solve the following system. That is x minus 3y plus z is equal to 4 minus x plus 2y minus 5z is equal to 3, 5x minus 13y plus 13z is equal to 8. Here are the steps and the solution. Again, choose two different pairs of equations and eliminate the same variable for both pairs. This will reduce the system to two equations and two unknowns. So first, let us denote the equations by e sub 1, e sub 2, and e sub 3. So denote the first equation by e sub 1. X minus 3y plus z is equal to 4. The second equation by e sub 2 minus x plus 2y minus 5z is equal to 3. And the third equation as 5x minus 13y plus 13z is equal to 8. And then note that our goal is to reduce the given system into two variables. Notice that we can eliminate x by adding equation e sub 1 to equation e sub 2. So we have the following. Since e sub 1 is x minus 3y plus z is equal to 4, and e sub 2 is minus x plus 2y minus 5z is equal to 3, when we add them, x minus x is 0 here, minus 3y plus 2y is minus 2y, z minus 5z is minus 4z, and 4 plus 3 is equal to 7. Next, we multiply the equation e sub 1 by negative 5 and add it to equation e sub 3 in order to eliminate x and get another equation in terms of y and z. So we have minus 5 times e sub 1 is negative 5x plus 15y minus 5z equals negative 20. And since our e sub 3 is 5x minus 13y plus 13z is equal to 8, when we add negative 5x with 5x is 0, 15y minus 13y is 2y minus 5z plus 13z is equal to 8z, and minus 20 plus 8 is equal to negative 12. Then denote the equation 2y plus 8z equal to negative 12 by e sub 5. So that is, we have e sub 5 is 2y plus 8z equals negative 12. Then we multiply equation e sub 4 by 2 and add it to equation e sub 5. So we have it here, twice of e sub 4, since our e sub 4 earlier was solved to be negative y and negative 4z equals 7. We now have twice of e sub 4 will give us minus 2y minus 8z equals 14. And then our e sub 5 is 2y plus 8z equals negative 12. So when we add them, we come up with the following. 0 equals 2. What does it mean? So meaning to say, in this system, each plane intersects the other two, but not at the same location. So therefore, the system is actually inconsistent. So the final equation 0 equal to 2 is a contradiction. So we conclude that the system of equations is inconsistent and therefore has no solution. So for our summary and conclusion, we have the following. For systems of equations in three variables, a solution set is an ordered triple XYZ that represents the intersection of three planes in space. A system of three equations in three variables can be solved by using a series of steps such that a variable is eliminated. The steps include interchanging the order of equations, multiplying both sides of an equation by a non-zero constant, and adding a non-zero multiple of one equation to another equation. A system of equations in three variables is inconsistent if no solution exists. After performing elimination operations, the result is a contradiction. Systems of equations in three variables that are inconsistent could result from three parallel planes, two parallel planes and one intersecting plane, or three planes that intersect the other two but not at the same location. A system of equations in three variables is dependent if it has an infinite number of solutions. After performing elimination operations, the result is an identity. Systems of equations in three variables that are dependent could result from three identical planes, three planes intersecting at a line, or two identical planes that intersect the third on a line. So for our exercise, we have the following. We're asked to solve the system of three equations in three variables. That is x plus y plus z is equal to 2, y minus 3z is equal to 1, 2x plus y plus 5z is equal to 0. The answer is given here. You can solve the exercise later on. And there's number 2, solve the following system. X plus y plus z is equal to 7, 3x minus 2y minus z is equal to 4, x plus 6y plus 5z is equal to 24. So the answer here is an infinite number of solutions of the following form. X, 4x minus 11 minus 5x plus 18. You can try to do this exercise. And for our references, we have Blitzer College Algebra Essentials, 5th edition, Person, again, Algebra and Trigonometry from the Department of Mathematics and Statistics, Mindanao State University, Iligan Institute of Technology. And for number 3, I made use of the following online textbook. So that ends our lecture 6. Then we will now have our last lecture, that is on lecture 7, which will be played later on.